Getting started with section 2.1, we are going to look at solving systems of equations. In this context, a system of equations is going to mean that you have more than one equation. Basically, there's going to be three different possible outcomes that will happen if you're asked to solve a system. The first outcome, this is going to represent one linear equation that's graphed. Here's another one. When you have two linear equations that you're trying to solve and you graph them and this is what you get, this is indicative of one solution. And that just means that these lines intersected at one spot. If you have two lines that are parallel lines never intersect. And so if they never intersect, then there's no solution. So now I have they intersect in one spot, they don't intersect at all, and then we have the case where you graph one line and then you go to graph the second line, and lo and behold, the second line and the first line are actually the same line. And when that happens, they intersect everywhere. So if they intersect everywhere, that would mean you have infinitely many solutions. Now, this still might not make too much sense to you until I start getting into some examples, but it's important to have this part of your notes done so you can come back and look at it and it will start to come together. There are going to be several methods you can use to solve a system. We're not going to learn every single method in section 2, but that's basically mostly what section 2 is all about. The first way we're going to learn is by graphing. We're going to look at the substitution method, the elimination method, and using a table on the calculator. Very important thing to remember, when you're solving a system, solutions come in the form of ordered pairs. Solutions come in the form of ordered pairs. So we're going to do this first example together where we're asked to solve the following system of linear equations by graphing. So I have two linear equations here. I'm going to label one of them with my blue marker. So if I go up 3 units, starting at the origin, 1, 2, 3, and then I use rise over run to plot more points, rise 2, run 1, rise 2, run 1. This is what my line's going to look like. I'm going to do my best to have a steady line. There we go. And then I'm going to do the next one in a green color. This one has a y-intercept of -1. Start at the origin, go down 1 unit, make your first point. Your slope is -2, so I can rise 2 and run -1. Rise 2, run -1. And then if I were to draw this line, there is my intersection right here. That intersection, that ordered pair, is the solution to this system of linear equations. And that happens to be -1, 1. What does this mean, though, when you find the solution? And it's an ordered pair. It means that if I were to plug -1, 1 into this first equation, I'm going to get a true statement. If I plug in -1, 1 into this statement, this equation, again, we're going to get a true statement. We were looking for an ordered pair that not only worked with the first linear equation, but it also worked with the second linear equation. So that's what we're looking for. Every time we're trying to solve a system, we're just looking for where two potential linear equations come together. It could be other kinds of equations too. It doesn't have to be linear, but we're just looking at linear now. Here's the second page. We're on page 31. A couple different examples where you're solving a system by graphing. If I look up here really quickly, I would have to distribute first and put this in slope-intercept form before I could interpret the slope and the y-intercept. The y-intercept here is 2, and my slope is rise 2, run 1. Here is my line. There it is. Get a different color line. Y-intercept is 2. Oh, look at that. Rise 2, run 1. Oh, it looks like we ended up having the same line twice. And remember before, if you have the same line, right, one on top of the other, that means these intersect everywhere. So that means that this has infinitely many solutions. There's more than one way to describe infinitely many solutions, so just want to make sure that you are prepared if you see it presented a different way. Some might not say infinitely many solutions. Some might say all real numbers. There's another way of saying it. I'm sure there are more, but I'm giving you two of the most common ways to describe when you have infinitely many solutions. Then we have down here another one. I'm going to have you just take a moment and pause and go ahead and graph these and then come back. Okay, so for the first one, my y-intercept is 1. My slope is rise 2, run 3. I'm going to go ahead and draw. There it is. And then for the second one, my y-intercept is 2. My slope is rise 2, run 3. You'll notice that there is something going on here that's a pattern. And the pattern is that these lines are parallel. They never intersect. And if they never intersect, then that means that there's no solution. I never wrote that up there, so I might as well do that. And that's a thing that can happen. Let's look at the next page. Last page. I think it is. If that was a mistake or not. But wow, is this the same as the page is on there twice? So we're going to just have to cross right through page 30. Oh, that was interesting. Okay, 2 and go to page 33. Looking at page 33. They're asking us to solve the following system of linear equations by using the table function in your calculator. So what I'm going to do is I'm actually going to pull up my Desmos calculator, and I'm going to put in my first line this linear equation. I'm going to type the whole thing out, y equals 5x plus 1. Then in the second line, I'm going to type out y equals 2x plus 1. The best thing to do with Desmos is after you draw these in and you'll see the lines in your graph, you're going to want to scroll around or zoom until you find an intersection point, and then you're going to hover your arrow over the top and it will give you the ordered pair that represents the intersection point. So what I'm going to do is I'm going to actually go over and do this in Desmos, and I'm going to bring a screenshot in. So give me 2 seconds. Here's the image of our Desmos. Notice that I went ahead, I put 5x plus 1 in the first column or row. I put 2x plus 1 in the second one. I wrote the whole thing out. And the color that I have here on the side coordinates with the color of the line. And then when I hover my mouse over the intersection point, it will give you the ordered pair. In this case, the ordered pair is 0, 1. Take a moment, you're going to put the video on pause, and you're going to complete the next set of examples. I want you to do the exact same process that we just did with Desmos with the last one. Remember that when you're putting 2/3 in, all you have to do is put a /, the same thing as a fraction bar, and that should take care of making your fraction. So pause the video, come back in just a moment. So here's what we would see in Desmos if we went ahead and put both of those equations in for both of the first 2 rows. Here is my graph, and my mouse hovered over the intersection point. It's going to tell me the solution to this is going to be 3, 3. 3, 3. One thing that's really important for you to know is if you look down at the bottom of this, there are some times when you might see questions that ask you if a system is one solution, or if it's infinitely many, or if there's no solution. Notice that there's lots of different combinations of check marks here. One solution means that it's independent and it's consistent. And if you were asked that question, it would be very straightforward. Is it consistent? Is it independent? If you have infinitely many solutions, that means that, again, it's consistent, but it's dependent. No solution means inconsistent.